Good evening, everyone. Please anyone confirm am I audible properly or not?
Yes, sir, you are audible. Good evening, sir.
Okay, thank you. Okay, so welcome to the session, and this session is for week 5. Okay, so agenda of this session is to continue wherever we have left in the last session, and we'll continue. We will finish that first, and then we'll go to the open session where we'll take questions and try to solve those questions. And in the last, I plan to cover. I plan to show you the metrics bit of metric calculus. We'll spend some time to that, and that we'll do in the last because some of you wanted to see how the loss derivative gradient of the loss function is being calculated, and so bit of metrics calculus is used there. I will try to show that here in the last of the session. Do in the last because it might not interest to everyone. So whoever is interested to see that can stay with us till last. Okay. So should we start now?
Sir, I have one quick thing to check before we start. Sir, today is the week 5 deadline actually, but what happened in the portal is that all our submissions are wiped out. Now, my question is that should we resubmit that, or will our previous submissions will be considered for grading, although the portal shows none of the submissions format? So,
No, no.
just out of
Your
checking on that.
your submission will be considered or
Considered, right,
whenever.
sir? Okay.
Yeah.
Uh,
So
No need
Hello,
to
sir.
redo, right, sir?
no need to
Hello,
worry
sir.
about it.
Hello, sir. I have a same question regarding this. I already, before the maintenance service, I already submitted the week 5 assignment. As far as I just take preparation. After that, I want to modify. Actually, I want to resubmit again the week 5 graded assignment, but all are wiped out in the portal.
Hmm.
How will I take no backup of week 5? Then how will I proceed? Deadline is tomorrow, I think.
Okay. So your previous answers, you are saying your previous answers are not saying on your portal, right?
No, it's
Okay.
all clear.
Okay, so
Suppose
that I have to convey to my team because that the one thing I cannot handle. Whether
suppose suppose there are 10 questions. Okay,
yeah, I got your point. I got your point. You're saying that you solved all the
uh,
questions before and you want to change
I,
answers to some of the
I,
questions, right?
yes, I want to add some more answers. Then how
Mhm.
can
Okay, okay. That I cannot handle.
and that
So
is
I have to convey
urgent.
this to the portal team. They only can help you in that.
Please, please, sir.
Yeah. So better to write to them and tell your problem. And as far as the concern is submission, your previous submission will be considered.
In the
So,
previous day, there is a MLF live session. I already convey this message,
so
and
better to write to the support team. They would be right person to help you regarding this.
will it be recovered within one day? I don't know. So
So
what to do
yeah.
now? Should I
So
again submit week 5 or what to do?
if you have remembered your answers, then please redo that assignment. Otherwise, I can this one is the thing that I cannot handle. So it's better to write to support team.
Okay, now actually I thought that if it will be recovered automatically, then maybe if I only answer 5 questions previously, then it will appear. The next updated version will not appear. That I just worried about.
So
They
Don't
sent
know.
I cannot help.
email informing us to take a screenshot or copy the answers. That's what they informed us actually through email, so that we can enter later. I don't think it will automatically recover.
Yeah, so deadline is today or tomorrow. Tomorrow, I think is the deadline.
Tomorrow, yeah.
Tomorrow.
So better to write to them. They only can help you in regarding this. Instructor cannot help in this.
Then please convey the message.
I can convey, but better if you write to them. They will answer you there.
Okay, will I?
Okay, so I think this will start now.
Yes, sir.
Okay, so you can see the screen, right? So in the
Yes, sir.
last, yeah, so in the last session, we were discussing about the linear regression problem, and we have seen how we can solve the linear regression, how we can solve the linear regression problem, and we make the assumption that the labels are associated with the features in a linear fashion, right? And that assumption we make and try to model this, and we use error functions to get the performance over the training data set, and then we try to minimize that error function, and that lead to the optimization problem, that a convex function optimization problem, right? And we have seen two methods to solve those optimization problem. One using normal methods, which actually takes the derivative and set it to zero, then find out the minimum of that objective function. And another method that we have seen is the gradient methods, where we start at some random point and then try to move into the right direction in the where it leads to the good, minimum point, right? And it works well in the case of where the optimization function is a convex function, and in our case, objective function is the sum of squared error, and that is a very nice function. Nice in a sense, it is a convex function, and there's only one minima, which is a global minima exists there. And so the gradient descent guarantees to be converged if we set the right parameters to that, hyperparameters to that. I mean, the learning rate and all, if we set appropriately, then it guarantees to the converge to the global minima. That's the one thing we have seen, right? And we have also seen the probabilistic view to that, and we assume that the data set comes from a function distributions, and it actually tries to find out the approximation to that function which generates the data, right? Because we don't know which functions generates the data, and we try to approximate that function using the data points, and that data points are actually coming from that function. So there are some data points we don't have the actual function with us. So using those data points, we try to approximate that function, and there we make a assumption that those are coming from a function, and that function is a linear function. But those data points have some noise with every data points have some noise associated with that, and we assume that a noise is a follows Gaussian distribution, Gaussian with zero mean, right? And there we have derived using the probabilistic view, and we have seen that it leads to the same problem that we have solved using the square loss function. So the square that also conveys that square loss is a better choice in the case of linear models, right? That still that point we have seen now, right? Now we will break this assumption that the labels are associated in a linear fashion to the features. Now we will break that assumption and we'll try to model non-linear relationship as well. Okay, so okay, so there's one trick for that. Okay, so idea is simple. Let's assume now we drop that assumption, and we make assumption that the data set is need not to be labels need not to be related to the features in the linear model. It can linear fashion. It can be any other relationship as well. Let's say some sign we will by equal by is following some sign relationship. So it can be by I is equal to sin xi, and they are coming from that relationship. So how to model such kind of distributions? So how to model it? Let's say this is the features. So any idea about that? But the good news is that we can even solve this kind of problem using the linear models. How we can do that? We have encountered such issues in the PCs as well, where we see that the data set is not features are not linearly related. Then we try to project our data set into a higher space, right, and then apply PCs. So same kind of approach will have here. Okay, so what we do, we try to transform our data set into higher dimensions such that this relationship within the labels and the features becomes a linear relationship, and then once that happens, we apply the same model there, right? This is the idea behind this, but we approach we see the different approach for the same problem. You can do in that manner as well. You transform each and every data points to the higher space, and in that higher space apply your model. That can be done, and even in the standard test book you will see that approach is followed. But here we'll see the same different approach for the same problem. Okay, it's the same approach. I mean the different approach for the same problem. Okay, and we will be using the kernel trick there, right? So what is a kernel function? Kernel function is a function that takes the two inputs from the input space and operates upon them, and the output is a real number, and this output is the same as dot product of the data points into the higher dimension space. So phi xi and phi xj will be data ith and jth data points into the higher dimension space, and the dot product will be the this phi xi transfer phi xj. So the output of this kernel function is the same as this dot product of those data points. And once if this follows for each and for all I and j, I mean, for all data points, then we call that functions to be kernel function, right? This is the definition of a kernel function. Okay, so before applying kernel trick to our linear regression model, what we will prove this fact as well. So the optimal solutions of the linear regression model, is actually can be written as a linear combination of data points. Okay, so what is the optimal solution of linear regression model? It is XX transpose inverse XY, right? So this actually can be written as the linear combination of the data points. Data points means that you can think those linear combination of the columns of X. So X is a D cross N matrix where each column is one data point, right? So here it is X1, here it is X2. Such N data points you have. So if you take the linear combination of the columns of X matrix, then that uh, so W can be written as the linear combination of the columns of X. So that we have to prove. So how to prove that?
Sir, one general question I have here. So how can we distinguish the polynomial regression from kernel regression here?
No, so this the same thing is happening, but the different manner, different approaches, but that leads to the same solution.
Okay, if I use either polynomial regression and kernel regression, I land at same solution. Is that
Same
what you mean to say,
solution.
sir?
Yes,
Okay,
yes.
got it. Okay.
But the
Sir,
different approach to
can
that.
I ask something? Polynomial is it's a kind of kernel, right? So there could be polynomial, there could be anything.
So
There are
what we
multiple
do in a
things.
polynomial regression, we actually transform our data point into a higher space and then apply the linear regression model there, right?
Correct.
That's it. Okay. In the kernel, we do the same thing, but we try to avoid the more computations and using some
Correct.
kernel trick.
Correct.
That's it.
Correct. 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 Okay. Got it.
Okay. Okay, so here we assume that we are trying to prove this claim that W star actually linear combination of the data point. So what we are trying to prove that W star can be written as the data matrix times some alpha vector, right? It's a coefficient vector. So that claim we have to prove. So how we can prove this claim? Any idea about it? So assume that W star doesn't lie in a linear combination of data points, or say W star doesn't lie into the span of x1 and xn, right? So it means that if you can take the projection of W star into this span. Let's say that projection is W. Let's assume that is a W prime. Okay, so that is the projection of W star onto the span of x1 and x2, span of those data points. Okay, so what I can write as W perpendicular, I can write as the uh, uh, that error, right? So let's assume this is your W somewhere, W star, and the projection on a span will be this thing. This is your projection of into the span of x1 and x2. So this I can call as W prime, and this error will be W perpendicular, or you can say this is the W perpendicular. What will be equation of this? This will be W star minus W prime, right? You can write this as this thing. These are vectors, right? So W perpendicular will be this. Okay, so what will be the value of W perpendicular with any? So this is W perpendicular with any xi. What will be the value of this? For all I.
0.
What? 0. Why 0?
Because it's perpendicular to the data space.
Yeah, yeah, of course. Because that's what we are doing here. It's the perpendicular to the span of those data points. It means that it's perpendicular to every data points. So W perpendicular. Okay, and transpose I have to take here. Xi is equal to 0, right? For all data points, it follows. Okay, so if I substitute this value as W star minus W prime transpose xi equal to 0, I can see that W star transpose xi is same as W prime transpose xi. It means that W star is nothing but W prime. It means that the W star lies in the span of the data points, right? So this is the claim. We are saying that the optimal solution obtained using the linear regression model using those data points, it can be written as the linear combination of the data points, right? So this is the claim that we have proved now. We will use this claim and we'll apply this in the higher space. Let's assume your higher space, the data matrix is phi of x. Okay, so here we are talking about since W star is now can be written as phi of x of some alpha, right? And this is the optimal solution which we have obtained using the normal methods, right? Normal equation. Okay, so if we substitute W star value to be phi x times alpha, I can write this. I can substitute this value, and if you do some of the just manipulation here, you can find that this alpha is nothing but k inverse y. And what is k here? What is k here? This is n cross n matrix. What is the values here?
X transpose X.
Phi xi transpose phi xa, ijth entry, right? This is the same that we have earlier calculated in the PCA, kernel PCA, right? So this alpha can be calculated using this, right? Once we have alpha and we already have the data points, we have alpha, we have the solutions, right? Phi and W star is phi of x times this alpha, and alpha is nothing but k inverse phi, right? But we don't actually want to calculate alpha. So actually we don't want to find the actual model with model. What we actually do, we can make the predictions for any. So this alpha we have calculated, we have phi, we can find. Okay, so we can find we have phi. If we have phi, we can find it. But if we want to avoid this, you can avoid. And what you can do, you can at last you want to make the predictions for some unknown data points, right? So you want to make the prediction for any test data points called xt. So this is again coming from the same dimensional space. And what I will do, I will transform this data point into the higher dimensional space. That will become phi of xt, phi xt. And then what will be the prediction for this data point? Is this thing, right? Because this is your model. Now if you substitute the value of phi star here, this is the linear combination of data points, that becomes phi of x and alpha, and I can write this as this summation alpha phi x I varies from 1 to n. If I take this inside, it becomes your k of xi xt, right? And this alpha I. So what's happening here? Here we are making prediction for xt, then we are finding the value of kernel function with every data points, and then multiplying it with the corresponding alpha I. So this actually tells the similarities with the similarity of xt point with xi point, and it actually gives the. Remember here we were saying that your W star is the linear combination of the data points, right? So we are saying that how much that data points is important. If this alpha value is greater, it means for any data points if it's greater value, then it means that particular features particular data point has the highest importance to decide that W size, right? So we check using this, we check the similarity of the unseen data point with xi, and this alpha I actually tells that the importance of that feature, that point, importance of that point xi, and that's how we make the prediction for an unseen data points.
Sir, I
Can
have
we
one
go
question
back
here.
Hmm?
Uh, Ravi, maybe I'll ask one question here in this formula.
Sure.
After that, we can go. Is it okay? Sir, when you say alpha indicates importance of xi, let's say I have alpha 1 and alpha 2. So,
Hmm.
am I going to say importance with respect to the magnitude of that alpha I? Is that how am I going to say?
Yeah, so here we are saying that W star,
Mhm.
whatever W star we are calculating, it's a linear combination of data points. Mean alpha 1 first data point phi of x1, right?
Okay.
Alpha 2 phi of x2, right? Plus
Okay.
alpha n phi of xn, right? So if some alpha I is greater, so let's say alpha 2 value is very high, it means that
Mhm.
this particular point has higher importance to deciding your model.
Okay. Sir, what if some alphas are negative? Then should we take absolute value, or should we consider just the
No,
plus or
just
minus
take a
also in the
negative value.
constraints?
Just take a negative value. If alpha comes out to be negative, you just take the negative value.
Uh, you mean to say should I consider absolute value, right?
No, don't take absolute value. Just take whatever the values calculates.
Okay, okay. Let's say, sir, if alpha 1 is given like 1, alpha 2 is minus 4. In this case, which feature like will be more important here? Is it alpha 2?
Yeah, for deciding if you check the importance, then you have to assume that the second feature takes. I mean, the second data points have the higher importance. It may be in the
Okay.
negative directions. Direction means that higher values maybe leads to the lesser values of labels, something like that. But it has higher importance.
Irrespective of the sign, we have to take the magnitude. Okay, got
Yeah,
it.
magnitude.
Thank you. Ravi, you can go ahead.
Can we go back a couple of slides, please? So here we are having the transformation of the points, and the transformation function is already decided by us, or it is not
No,
decided
we
by
need
us?
not to decide. We just assuming that there is some phi which
Mhm.
transform our data points to some higher dimension space.
Okay.
Okay.
This is a
And then,
theoretical calculation we are starting off with. Okay.
yeah, and we have already proved this claim that the optimal solutions is actually a linear combination of the data points, right? Now
Correct.
data points become your phi of x. So my W star can be written as phi of x times alpha, right? So this is a linear combination of your data points.
Sorry, that part, W star is equal to 5. Okay. X alpha. Okay. The alpha is what you have written over there. Okay.
Right?
Okay. And K is again the covariance matrix.
Not a covariance matrix. This is that K matrix we call it,
Okay.
right?
Okay.
This is phi of x transpose phi of
Okay. Yeah.
x.
Kernel. Okay. Kernel matrix. Okay.
Could you go back one slide? So this phi of xi transpose alpha is sort of this W prime.
No. Here we are claiming that this W prime is same as W star. So what we are calling W prime to be W prime, we are calling the projection of W star into the span of x1 xn, right? And here we are saying this W star transpose is same as W prime transpose xi. So it means that your W star is same as W prime. And what is W prime? Is the projection on into the span of this thing. It means that it lies in the span of this thing. Okay, and it means that W star it lies in the span of X data points, right? It means that W star
We
can be written as
initially assumed it did not lie, and then we took its projection, and
projection.
then we found out that it is actually the same, one and
Same
the
thing. Yes, same thing.
Is that why the norm of W star and W prime would be the same?
Yeah, because now they are same. It means that their prime or their norm will also be same. They are the same vector. Here we have proved that they are the same vector. They are not different.
Okay.
Okay.
Okay. The next slide, we are actually taking the transformation and then
Transformation.
phi x.
Yeah. So we are assuming there is some we have transformed our data points to higher space. Now we are applying the your linear regression model there, right? And we have already seen this
Okay.
optimal solution is linear
Can you slow down
combination
here
data
a
points.
little bit, please? W star is equal to pi alpha, pi x alpha is what you had written at the top.
Hmm.
Now W star, how did it actually become this phi x transpose?
This one.
Yeah.
So what is the solution that you get for using normal equation W star? This is XX transpose inverse XY, right?
Yep.
Remember,
Okay,
so
the
your x now is phi
okay,
of x,
x is phi of x. Okay.
right? So that's what I brought written here.
And the below one is w. The above equation is what you put over there. W
This
star is
one,
equal to
this
phi
I've just
alpha. Yeah,
substituted this value
substitute
from
that over
here,
there. Okay.
and then do some do some algebra and not algebra, just some manipulation of the terms, and you will get that alpha is nothing but k inverse y.
Okay.
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 And that's not hard to see. You just multiply phi of x transpose both sides.
Okay.
So this will become identity matrix, and this will become your phi of x transpose, and this is already phi of x, right? And here it is, this become identity, this become phi of x and y. And if you again take phi of x transpose, multiply it by phi x transpose, so this become phi of x transpose, phi of transpose, that is your k matrix, right? And this is again your k matrix, so k times k alpha times, here again this become k times y matrix, right? So this you can write as k
So
alpha equal to
first I
y.
multiply both sides by phi alpha phi x, is it?
Phi x.
Phi
First
x
you are
transpose.
multiplying it by phi x transpose. So this becomes identity because this is the inverse of that, right?
Okay. Okay. So that becomes okay. Then I'll
Yeah.
have to return
And
this.
then again you multiply it by phi x transpose.
So k
So
square alpha is equal to
k inverse y. Alpha you can write as k inverse y.
okay. So k square alpha is equal to ky is what we will get. K and k you directly knock off on either side, or how is that?
It's just the inverse of you
Okay.
multiply with the k inverse, right? K inverse exists, then you can do that always.
Okay. Okay. Okay.
Okay.
In the next slide, you are actually going for the prediction, right?
Yeah, since it means once we have find alpha, if you try to find w your model, then you have to use phi of x times alpha, right? Phi of x times alpha. But you want to
Yeah.
avoid this calculations, right? This is the whole
Yeah.
idea using kernel tricks. So we
Correct.
actually don't find the model. What we do, we make the predictions for any unseen data point.
Mm-hmm.
Okay, and for finding this, what is the prediction? If your W star your model, then what is the prediction for any data point? This
W phi alpha phi x alpha.
W transpose phi of that data points, right? It's just a model. This one model W1 x1 plus W2 x2 plus, this is your model, right? This was your model
Yeah.
for
Yes. That is W star. Correct.
making any prediction. You just put the value inside this and just get the output, right? So this is
Yeah.
what in the vector form. Here the data points become phi of xi. That's it.
Okay. Okay.
And just do the manipulations here, and you will get this same as this thing, alpha
So
I times k of xi xt.
so W is the weights, and phi xi is again a transformation, correct? So
Yeah,
should,
transform. This
I
is your
can't use the
transform data
original
point.
points. Yeah, I can't use the original points here,
You
right?
cannot use because you are applying your linear regression model into the higher space. You're
Correct.
not
But
applying your models linear regression model into the original feature space.
correct. So I need to know the transformation function here, isn't it?
If you want to use this, then you need w and you need phi as well. But if you do this manipulation here, you will get this expression in the last. Here you don't see any phi, right?
I don't say phi. Yeah.
Yeah, so you actually don't need phi to make prediction for any data point. You just need to know k, kernel function.
Sir, K is n cross n. Alpha is also
This is kernel function. This is not matrix. This is kernel function.
yeah. Sorry, correct. But alpha is n cross one, right, sir?
Alpha is n cross 1 vector.
Correct. Okay. So for each point there is a weight.
Yeah, associated with that.
I don't understand what is XT.
What is
Saying
X?
K, XI, XT.
This is your unseen data points. It's coming from RD, any d-dimensional data points. So what you do, you transform this data
It's
point
coming from?
at your input space, feature space, right? RD, d-dimensional space.
It's an unseen data point for which we don't have a yi.
Yeah, YT or
So test data, right? That's why it's like test data.
yeah, test data point. Is it clear or not?
The weights part is clear, but when it comes to k, xi, xt, I still am conflicted about how I actually end up with the function on that. I'm not able to recollect from the past one also.
This one, this thing,
Yeah, yeah,
this
That
thing.
is
k, yeah, yeah,
that is you remember Ravi, 1 plus x1 x2 square, right? Things like that.
yeah. But that is a polynomial function, Navasu.
This also can be polynomial.
Yeah, so we need to know the transformation. No, that is what I'm actually.
No. So for any okay,
Hmm.
so for any transformation, there is for any transformation RD to RD, there is a kernel function associated with that, right? So
Correct.
kernel function means that if you are let's say you have two definite data points x1 and x2. So what phi does it sends to some other input space. So let's say
Correct.
one x1 x2 x1 square x2 square some x1 x2, right? This is
Correct.
a polynomial transformation of degree 2. So this is your phi, right? For corresponding to this polynomial transformation, you have a kernel function which actually takes 2 points xi xa, and it's the same thing as 1 plus xi transpose xa square. If you calculate this, you will actually will give you value of phi of xi transpose phi of xa.
So when that means we know the polynomial and the order of it, the transformation.
Yeah, that we need to know which transformation we are applying
Okay,
corresponding to
that was
that
my question
transformation,
actually.
which is the appropriate kernel function.
Yeah. That was my question actually. Yeah. Um,
So any other doubts in this?
So what are we doing exactly when we are saying alpha 1 into kernel? I'm still okay. I'll think about it. It's fine. Fine, go ahead.
Okay.
Um, would it be, would question 8 of practice assignment 5 be something on these lines? I mean, if you could please do it so that this makes sense. I'm not sure
Okay.
if
Let
you
me do
relate
that
it.
question. Let me give me
Sir,
1 minute.
one last question. One last question. So when we do the polynomial regression, which is basically 1x and x square we take, and then uh, will that, if I did it that way, if I take a dummy problem and do it that way versus if I use this kernel, will I get the same response? Will I get the same answer? Is it the same thing?
Okay, so in practice, what happens? This kernel function may be defined in some different manner in practical scenario. I mean that if we have written here, we have written 1 plus. Okay, so there's lots of background noise. Can you please mute?
Vasu, echo is coming from your side. Yeah, echo. Yeah.
Yeah. So if you there's some different ways of writing this kernel function as well. In some standard text, we call if you follow the sklearn as well, there you will see that kernel function is nothing but c plus d x xi transpose x z raised to power t. So those constant actually has to be defined using some cross validation techniques, right? But for standard functions like Gaussian kernel or some say polynomial kernel or standard kernel, if you do on the toy data set, you may find those answers or those optimal solutions are actually the same solutions, not different.
They were in MLF. We were taught polynomial regression, so that was very
Mhm.
straightforward. So I was
Yeah,
thinking if I could do it that way because it's a very simple thing. Versus, let's say I use this 1 plus x1 x2 square as a kernel, polynomial kernel. I wanted to know whether I'll get the same answer. Maybe I'll just try and let you know.
yeah. You can try it out, and there's most chances that you will get the same answer, not the different.
Okay. Thank you.
Um, alpha is a n by 1 matrix, right? Or
Yeah,
am I
alpha by
mistaken?
n by 1 matrix, sorry, column vector.
It's a column vector. Then the graded assignment problem 6 and 7, it is written this way. I'm little conflicted about this one. It is given as where is that? Yeah, sorry, 6 and 7. W is equal to x into it is given as a row vector.
Okay,
Is there a transpose on top of it?
No, that's the problem. That's the reason why I'm a little.
Okay, so it may be the case that's wrongly configured or wrongly given. So which question? Activity or graded
No,
assignment?
graded assignment question 6.
Let me check. Okay, so there question number 6, right?
Correct.
Okay, so there is one thing. It should be phi of x, not x, right? Because you are saying W is to be linear combination of the data points, and your data points actually has come into the higher space, right? And there it should be phi of x, not of x.
Okay.
And this
But
should be your alpha transpose. That is right. This should be transpose.
yeah, and the 7th question, it says prediction for the data point, that particular transpose.
Yeah,
So,
transpose.
so that's the data, as in those are the D of the data, right? Data point, correct?
Yeah, these are your 5 features. So your data points are coming for
Okay.
prime dimensional space.
Okay. Okay.
Right. So there's the one thing in here. It should be phi of x, where this is written W equal to x and this alpha, right?
Yeah. Yeah.
So
Yeah.
this should be phi of x times alpha transpose. I mean this
Alpha
transpose
transpose.
of this
Okay.
vector.
Okay.
Okay, so I will try to correct it.
Yep. And
Okay. Okay, so practice assignment question number. Which question you told? Question number 8.
8.
Okay, give me 1 minute. Let me open my whiteboard and then we'll solve this question. Okay, so can you see the whiteboard?
it's coming up.
Yes. Yeah.
Yep.
Okay, so this was your question number 8. So it is saying that you have applied a Gaussian kernel regression with the parameter this to the following data set. Okay, with 2 features. So you have 2 features. So this x is your 2-dimensional. Here this x is 2 cross 4 matrix. So 4 data points you have been given and 2 features, right? So this is your first data point. This is your second data point. This is your third data point and 4th data point. And this is the corresponding label. So first data points are label 2.1 and similarly all 3 data points, right? Now, so this phi x should be written as this phi of x. So here this w should be phi of x times alpha, right? And the alpha vector is given to you this 1.4 minus 1, this thing 1.4 minus 1.420, which is obtained as using this method that we already know, right? Now k is the kernel matrix. What will be the prediction for the data points? Okay, so how you will find the prediction for the data point? So you may, the prediction is actually alpha I, k, xi and xt. So this is your xt and you sum over all the data points, right? So what is your kernel function in this case? What is kernel function in this case? You have been given Gaussian kernel.
It would be 1 by square root of 2 pi sigma.
So this is e raised to power minus norm of xi minus xj square upon 2 sigma square, right?
Square.
And sigma square is given to be 1 by 2. So this will e raised to power minus xi minus xj norm square, right? This is your kernel function. So what you have to do, you have to calculate the every, this is xi xj. So you have to find k x1 xt. So xt is your xt or this point 1 comma 1. Right?
1 second, can I interrupt, please? Why
Yes,
did you
sure.
remove the 2 sigma square directly? Is it proportional or how?
2 sigma square value is given to be 1 by 2.
Okay, half. Okay, sorry.
Right? So what is your x1? X1 is this point, right? This point. 1, 0.
1,0, yeah.
So this is your 1, 0, and your test point is 1, 1, right? So if you take the norm of this thing, what will be the norm?
1 square. Norm
1,
is
right?
1, yeah.
1. So kernel value for the first data point and the unseen data point is what? Right?
E power minus 1, yeah.
Right?
Repeat that. What's that? I didn't get it.
So you have to calculate this value. This is the kernel function value for xi and
XT.
xj, right? So we are calculating for k, x1 and the unseen data point xt. So this is your unseen data point and this is your first data point.
Yes. Yeah.
So you have to calculate this norm. What is the norm here? 1, right?
0 square plus minus 1 square, okay.
So this become 1 e raised to power minus 1. Similarly, what will be k x2 xt? What is your xt? x2? 0, 1.
0, 1.
0, 1, right? So 0, 1. So you will do 0, 1 and 1, 1. What will be the norm?
1 again.
1 again, right? So k x2 xt will be e raised to power minus 1 again, right?
Yeah.
Similarly for x3 is 1, 1. The
So it's
same
e power
as
0.
the unseen data point. So what will be the norm?
E power 0.
E raised. So this will become 1, right?
Yeah.
And for the fourth data point is 0, 0. So what will be the norm?
2. E power minus 2.
So this is 0, 0, 1, 1. So this will become e raised to power minus 2, right?
Yeah.
x4 and xt, right? So, and what is your prediction? This is alpha 1 k x1 xt plus alpha 2 k x2 xt, right? Plus alpha 3 k x3 alpha xt plus alpha 4 k x4 xt, right? So what is alpha 1, alpha 2?
The
Can
1.2.
you please
So 1.
how you get e to the power minus
Sorry, how did you get
minus 2 value?
this one?
Yes.
This is the norm of these data points.
K x4 inner product.
This is just xi minus xi will be 1, 1, right? Xi minus xi. So xi square plus x2 square root over that.
Oh.
Right? So what is alpha 1, alpha 2 in this case? This is given to you, right? 1.4 minus 1.4, 2 and 0, right? So the fourth one will vanish. And first and 2, if you remember, this is 1 e raised to power minus 1, e raised to power minus 1. So and the coefficient is plus minus. So this will again vanish,
0.
right? So you will get 2 times 3, 2 times this value. So you will get the prediction as 2.
Okay.
Got the point?
Deceptively simple.
Yeah. So the answer is easy there, but yeah. So one point here that it should be 5 in the question. It should be 5 of x. So here, there. So in the question, it should be rather than x alpha, this should be 5 of x times alpha. I will correct it in both practice and graded assignment.
Yes, please.
Sir, one doubt.
Hmm?
Sir, only when the, here in the question it's mentioned that it's a Gaussian kernel regression.
Hmm.
Only if it is mentioned, then we can go about doing like this, right?
Yes, of course. Otherwise, you don't know which kernel you have to apply.
Apply, okay. Okay, sir. Yeah. Thank you. And not related to this, in activity question 5.5, question 5, I have a doubt.
Give me one minute. My portal is not getting login.
Uh,
Okay, so are you able to log in the portal?
yes, sir.
Actually, I am not. Okay, now it's coming up. So activity question, which?
Yeah, it's a true or false, sir. 5.5, question 5.
Okay.
A gradient descent takes more number of iterations to converge to local minima than stochastic gradient descent.
So what do you think? It should be true or false?
The answer, it says it's false, but I think it's true.
Okay, so how do you? What do you mean by iteration in the this gradient descent method? Whenever you update your weights, that is one iteration.
Yeah.
And what you do in your stochastic gradient descent, you make the batches and then update your weight vectors, right?
Yeah.
So in that way, you have to make more iterations to converge to your global minima. So stochastic gradient descent actually takes more on average, not always, but most of the time. It takes more number of iterations to converge than the gradient descent.
Okay, we follow stochastic gradient descent because we don't want to do it for every single point, right? Like we make it into batches and do it. Then what is the use of doing a much more complicated thing, sir?
No, it's not
Like,
complicated one. It's just because gradient descent is very it takes the cost of computation cost with that algorithm. Because remember, it calculates the gradient at each and every points, right?
yeah.
Okay, so here if you are making 100 iterations, then you have to calculate 100 times your gradient of that loss function at that point. That is very computationally costly. So remove that cost, computational cost. We actually don't make use of every data points. What we do, we compute the gradient at each point, but using some data points, but some
Okay,
subset of
sir.
data points, not all data points. So that's how we get reduce computational cost to some extent.
Okay.
So, sir, tell me if I've understood this right.
Hmm.
So, see, it may take more iterations, but because it's much small, you're doing it on a much smaller sample, it is likely to, in terms of time, it may likely to converge faster actually.
Yeah, in terms of time, that is different thing. In terms of number of iterations, then stochastic gradient descent takes lots of
So
iterations to converge.
that's fine, sir. That's fine because
Yeah, but in terms
because,
of time to run that algorithm,
yeah,
stochastic will be faster than gradient descent.
correct. Because when we look at computation efficiency, we look at time complexity, right? So,
Yes, yes.
so that one question, sir, when Prof said actually 1/t and average over 1/t, can I treat that, because last time we had this big discussion on how exactly at what stage will the weight get updated, batch
Okay.
size versus epoch. So can I consider that t as number of epochs?
Okay, so actually I don't remember what professor has mentioned there,
Okay.
but
Okay. I'll post it on discourse.
okay. Okay, please post on the Discord. I have to cross check from the
Yeah,
lecture.
because when I think of it as an epoch, each one being an epoch, then that formula makes sense, because we are taking the final. See, you get the final weight. The average makes sense only when you average it on the final weight vector you get, right? So,
So generally, if the algorithm says that you just keep on updating your weights every time using those many batches, and the final weight vector will be the last weight vector. It's not like taking average and all. Okay,
correct.
so
Last final, if I do it over, let's say 10 epochs or whatever, a k number of epochs, then I take the average of all the vectors I get at the end of each epoch, right? So that is.
then if you're taking average of the weights that you got at the end of the each epoch, then that t will be the number of epochs.
Correct. So that's what I think Prof meant it. He didn't get into these details, but that's what he meant it, because that average makes sense only when you do it on the final weight vector.
Okay, got it.
I'll post it on Discord.
Sir, I have one question in gradient descent algorithm.
Hmm.
So far, we have seen the variant to update the weights in the each iteration, which is typically applicable for a linear regression or logistic regression equation form. Actually, I'm just curious to understand if the same format of gradient descent is applicable for, let's say, XGBoost or random forest or decision trees. Actually, just thought of checking with you on that, or is it something that is going to come up in the upcoming weeks?
Okay, so ensemble method you will see in the week 11, but just one clarification there. Those
Mhm.
methods are ensemble methods, and we make use of different estimators and combine those results. Like in general, we combine the results using decision trees.
Right.
So there we don't use such methods like gradient descent all. We actually uh, train different estimators like decision trees or KNN, whatever we use. Generally use decision trees and then combine those results. And there's different ways to combine those results. So we don't use such techniques like gradient descent and all in those ensemble methods.
Okay.
Okay, so
So just
there's
curious to know.
one
Uh-huh.
ensemble method technique which is called gradient boost, which makes use of the gradient, but not of the
Uh-huh.
gradient descent technique.
Hi, same question I'm going to ask you, sir, actually. Yeah.
Yeah, so
Okay. Got
that we can discuss in week 11.
understood, sir. Thank you so much. Yeah, got
Okay.
it.
So I think you have posted that on this course as well, right?
Yes, sir, exactly.
So yeah, so that
Thank you for the
gradient
clarification.
boosting actually names comes from the gradient terms, not from. It doesn't mean that it
Okay,
uses
okay.
gradient descent to
Got
code
it.
that algorithm. Okay.
Got it, sir. Got it. So sir, just to simplify this, so none of the ensemble learnings which use decision trees as a base classifiers, they will
Mm.
not use gradient descent algorithm for optimization. Is
No,
that
no.
statement
So
correct?
yeah, so there we train decision trees, and
Mm-hmm.
how we train decision trees that we will again see in week 7.
Okay.
Decision tree is I think, is a completely different algorithm. It uses entropy, cross entropy as a
Yeah,
loss
yeah,
function.
different. So you'll see in week 7 how
Huh,
decision
that I
trees are
understood,
trained.
sir. So definitely they will not make use of gradient descent algorithm. That I can
No,
say, sir, right, sir?
no. Yeah, yeah.
Got it, sir. Thank you.
So any other doubts in this kernel regression and all? Or any activity question or practice question
This,
in
this
week
was
5?
this was which question, sir? AQ, which activity?
Which question?
This one, the one you are showing on the slide.
So
This was
this is
AQ.
the practice question, question number 8.
Oh, practice.
Sir, again, I have done one small test kind of a thing. I think in previous session also I have asked one question. In MLF, the formula for gradient descent is mentioned in the different formula. I think you kind of mentioned the dimension could be n cross t there, right?
Yeah, yeah.
I kind of took a small toy example and I tried to work out on both equations, sir, like n cross d format and d cross n format. I think both are not giving me same answer actually, sir.
No, that they definitely should give the same answer. You must be doing some different. You must
I'm
be doing
not getting,
something
sir,
wrong
for
there.
some reason actually. I mean, if time permits, maybe towards end of the session, probably I think we can take some small, one or two data points example, and we can, I think,
But it's just a
work
matter
out.
of convention, right? If you take n cross d matrix or d
I
cross n
agree, sir.
matrix, it's
That is
just a
what my
matter of
understanding
convention.
also. That is what my understanding too. But I think I'm getting different answers. Even I
So
don't know where I'm
you
getting
must be
doing a
doing
mistake.
something calculation mistake there. Otherwise, they must
Okay.
be same answer, not a different answer.
Okay. Okay.
Okay, so should we move to the that matrix calculus part that I planned for? If you don't have any doubts, we can move to that. Otherwise, okay. So let me share that screen. Okay, so this part actually, if someone is not interested, they can drop off. This is actually related to how to do the derivative of a loss function with respect to the vector function, right? That we have come across in we try to find the gradient of a loss function with respect to a vector weight vector, right? So how to do that? This just bit of calculus is used. Okay, so that I want to explain here. That is not interest of not interest, then you can drop up, and because that's not in your course, it's just uh, uh, some knowledge of matrix calculus is used there, right? So let me present that. Okay. Can you see the screen?
Yes. Yeah.
Okay. Yeah, I'm muting everyone, and if you want to speak, you can unmute and then can speak. Okay, so here what we just briefly explain the derivative, how to find the derivative of a vector function with respect to a vector or a matrix with respect to a vector, right? So I will just try to explain those things, and I won't go the proof part of all those things. You can try out by yourself how the proof comes in. Okay, so here is something. So there's two function. One is scalar valued function. Another is vector scalar value. I mean the vector valued function. So the difference is clear, right? The scalar valued function means the output is always a scalar function. Whatever the input is, the output is a scalar. Then it's called a scalar function. And the vector function, when the output of a function is a vector, then we call that as a vector valued function or simply vector function, right? Now, you must have seen in the different variables. So here we are assuming f of w. Let's say f of w is a f of w is a scalar function which and the input is only one dimensional input. It means it's a variable. It's a one input or say one scalar. I mean, what is that called? I mean the input is only one variable, right? So it's one variable scalar value function, and if we take the derivative with respect to a that variable, then it actually gives the how the function changes as w changes, as that variable changes, right? Or that function actually is a curve in that two-dimensional space. So this is your w, this is your f of w. Then this f of w will be some function. Let's say this is function, and if we calculate the derivative at some point, so it at that point is actually gives the how the function change. It means if you change w little bit from that w, then how the function is changing, right? So how the function is changing, that is actually calculated using the derivative function, or in the simple manner you can say the slope of that function tangent at that point. So if you can find the tangent at that function and that slope of that function, right, tan theta, so that is actually nothing but the derivative of this function. So this in simple case you must have seen in the math courses. And if there are more than two variables, let's say the function is more than two variable function, then you calculate the derivative with respect to each of these variables, and those are partial derivative. It means that so this will be a surface or any curve into higher dimensional space. In this case, if there are three features, then it will be surface or any curve into the four-dimensional space, and right. And if you take the derivative of that function with respect to the variable w1, it means that if you make the change into only this direction, w1 direction, then how the function is changing. Or the other way to look into this, uh, you just take the plane parallel to w1, right? So if you are calculating the derivative at point a b c, just take w1 equal to a plane, this plane, and cut your surface. So if you cut the surface using this plane, then you will see a curve, right? That curve, and at that in onto that curve, there will be point ABC, and then make how the gradient is how the function is changing for that curve around that point is actually calculated using those partial derivative. And similarly, for you can find with respect to any two variable w1, w3, right? So this is the idea behind derivative and the partial derivative, right? So you already must be familiar with all these things. Now gradient, how you find.
Can you slow down a little bit? And the place where you said multiple variables are there, that is clear. But after that, we go for the partial derivatives, is it?
Yeah, partial derivative for because now you have more than one variable, right? The function
Yes.
takes more than one variable. So if you take the part derivative of the function with respect to w1, so it's just think as how the function is changing when you make the changes into w1 direction, right?
Okay.
Okay.
One direction each
Similarly,
time. Okay.
yeah, one direction each time, right? So think as like cut your surface in using that plane w1 equal to a plane. Then that the intersection of the curve and that plane will be a curve, right? That surface and the curve. Think is like you have some paraboloid kind of thing in three-dimensional space. If you cut it using a plane, let's say plane parallel to the x by z plane, then that intersection will be some curve, kind of parabola. So there will be point A comma B comma C, and then you will find the tangent at that curve and the slope of that curve. That will be your partial derivative thing. It's just like same thing, but 4 different directions. We have different values. Then we find the partial
It
derivative
sounds
rather than
like
derivative.
directional derivative, right?
No, no, it's a derivative. Direction derivative is a different thing.
Okay.
Okay, so what is the gradient of a function? Now, so scalar function, we always calculate the gradient. Gradient actually gives is the same. So this is your scalar function. So that gradient is defined as this thing: del f by del w1 I cap. I mean the directions. Here it will be w1 cap plus w. Sorry, this will gonna be a scalar. It's a vector quantity. So this will be del f by del w2 and del f by del w3, right? So transpose. Okay, so I've already written this here. So this is gonna be a gradient, and it actually gives the direction in which the function changes maximum, right? Let's say you have this scalar function, and if you want to find the gradient at this function, so it will be in the direction. It will be a direction in which the function changes maximum. So so gradient will be something like this, right? So this will be your gradient of for this point. So any scalar function, at any point, if you you want to find out the gradient, it will be a vector quantity, and that vector quantity gives the direction in which the change of the function is maximum. Okay, and it's actually given by this vector. Okay, so here is one question for you. What will be the modulus for this this vector function?
A square plus B square plus C square.
So that is okay. So this is your gradient. If you take the modulus, it will be just del f by del w1 whole square plus del f by del w2 whole square plus thing. So what this quantity gives you? Have you gone through vector this gradient thing, directional derivative thing in math courses?
Yeah, yes, sir.
So what this modulus of a gradient gives? This is clear, right? We calculate the gradient for a scalar function, and the gradient is actually a vector quantity, and this vector actually gives the direction in which the function changes maximum, right? And this is given by this vector.
It will
What
give
is
the
the modulus?
maximum. It will give the maximum rate of change.
Yeah, it's the rate of change of function, right? So the modulus actually gives the rate at which the function changes in that direction. So this is the rate of change in that direction, in gradient directions. Right? Okay. So this is okay. This you must have seen. Now derivative of a function, scalar value function. This is your scalar value function. Now we have seen the derivative with respect to a single variable, right? The scalar value scalar. So here we have scalar function, and we are taking derivative with respect to a scalar itself. Now what if I take the derivative of this function with respect to vector? Let's say this is your vector w, and if I want to find the derivative of f with respect to vector w, this is your vector now. So what will be this thing? So this is defined as something like this. So this is your function. W is w1 plus w1, w2, w3. This is your vector, column vector. Okay, so here we are all following numerator layout notations. There's two ways to denoting all these things. One is numerator layout, another is denominator layout. So this is the matter of layout, right? So I can write this as something like that. Wf of dw1. So I will take all those derivative of the function with respect to all the elements. So there are the three elements in the vectors w1, w2, w3. So I will take the derivative of with respect to all these function and store in a vector. So this is your nothing but this is your del f by del w, the derivative of the function with respect to this vector, right? And so this is called numerator layout, where you just transform these things. So it is nothing but this product is called Chronicle or Chronicle. I am not remember the word itself. Chronicle, I mean Chronicle product it is called. So what it does, in this particular layout. So there's two ways, right? For the layout, you can even store into like this, or you can even store like this, right? Both are acceptable. This one is called numerator layout, and this is called denominator layout, where you just so it's just a transfer from one another, right? So we actually follow this particular layout. Okay, so it's actually what's happening here. We just take the transform of this thing. So this is just, you can think as day by del w1, del by del w2, del by del w3, and take the Kronsky product with with this whatever you have f. Okay, is that clear?
Yes, sir.
Clearly, could you please take an example?
Okay, so example can be something like that. Let's say you have a function, you have a function f of let's say x, y, z. These are three variables. This is something like x square, y, z. This is your scalar value function, right? Can you mute yourself, please? And your vector is x vector, and it's vector x, y, z. Now you want to find del f by del x. How you will do that? It just so you took the Cronker product. So this will be del f by del x, del by del y, del by del z, with the this f. F will be x square y z, right? So if you do this Cronker product, so this is just del y del x. So this will be 2x y z, and this will be x square z, and this will be your x square y, right? So this is the derivative of the function with respect to vector x vector. Okay, so this is your
We have
derivative.
just multiplied the gradient with the function itself.
Multiply of the gradient. No,
This,
these are the partial
the
derivatives.
partial derivatives are the gradient, right?
No, these are not full gradient. Gradient, the vector itself is called gradient. So if you find the
Yes.
gradient of this function, so that will be del f by del x, del f by del z, del y, or del f by del z. That column vector gonna be, or say this del f by del x transpose gonna be your gradient in this case.
Yes. And haven't we multiplied that by the function itself?
Yeah, this is function. This is Cronker product, right? So what is Cronker product? So if you define as
No, sir, we have to still multiply it with the function, right? What you have done. You put it as a
multiply.
numerator.
It's not multiply.
Yeah.
It's just the operating. This is your operator. This is your operator, right? This is your operator. It's not a value. This is operator. It's operating upon this function.
Okay. Okay.
Okay.
Okay. Got it.
Okay. So what is Cronker product? So a Cronker product B is something like that. So you have a matrix. Let's call those element A11, A12, A21, A22, right? And with me, so it is some same as A11 times B, A12 times B. So A21 times B, A22 times B. So this is called your right. So what will be the dimension of this matrix A times B? What will be the dimension of this matrix? Let's say A is your n cross M matrix, and B is P cross Q matrix. What will be the dimension of A cross B?
N cross Q, right?
No. This is not that product. This is not.
Sorry.
This is something like this is defined something in this manner.
N cross M.
N cross M is the A matrix. B matrix is P cross Q. So if you think is like let's say B is something like that. B1, B11, B12, B13, B1, B21, B22. So this will become now. This will become here. So this will become.
Yeah, 4
this
by 4
will become,
matrix, right?
This will be two by two matrix. This is 2 by 2 matrix. This is 2 by 2 matrix. This is again 2 by 2 matrix. So how many elements are there? 4x4 matrix,
4 by
right?
4 matrix is what it will become, right? Yeah.
Yeah. So in general, if it A is n cross m matrix, B is p cross q matrix, then what will be the dimension of this matrix?
NP into
NP
MQ.
by MQ.
Yes. Yeah. NP times MQ, right?
Okay, that's interesting. So on this,
So remember, n rows. So n rows will come from here. N rows, right? And again, those n rows is multiplying with p rows here.
and what
So
is the
that will.
operator between A and B called?
This is, I'm not remember the actual name.
Called
So this
it's
is
called it's called Kronecker operator, sir.
Cron-cut product. Cron-cut
Kronecker.
product, I mean.
Kronecker product. Okay.
Right. Okay. So this dimension is clear, right? This will be NP times MQ. So here A1
No,
will
sir, could
multiply
you
by
just
P.
explain this part again?
Which part?
How it has become NP cross NQ?
So here, how many rows will come in general? How many rows will come? And here I'm saying A to B, A11, A12, A21, A22, right? And it's multiplying by B. So here it is A times B, this B, and B. So how many rows in this matrix? In general, n rows, right? Now, so
Yes, sir.
all those n rows are multiplying by rows of B.
Hmm.
So how many rows for B? So how many total rows will there? If B has P rows, this will be NP rows, right? In this matrix, NP rows.
Okay.
Similarly, how many column will be there? For each one of these will be, how many such columns will be there? This will be M for this, and each column is multiplying by the column of B. How many columns in B? Q columns. So NP
Okay.
times
Yes.
MQ will be the
Yeah.
dimension of A cross B, right?
Okay, sir. Oh.
So remember, in the numerator layout methods, this is notations, numerator layout methods, we do that upper things remain the same, and here we take the transform of the vector. Here, if this is the vector W here, so W is your this vector, W1, W2, W3. So this is column vector here. We take the transpose of this and take the operator. So if I take the operator, it will become dw upon dw1, d upon dw2, d upon dw3, and we take the transpose of this because it was column. Now it becomes row vector, and this thing remains the same. And we do the conquer product here. Okay, so what will be the conquer product here? In this particular case, it will be just del f by del w1, del f by del w2, and del f by del w3. Right? So this become your del f by del w, del w. Right? So actually, this is nothing but the transpose of the gradient, right?
Yeah.
Right. And sometimes this is called tangent vector. So tangent vector, you can think like you have some position vectors. Like let's say your position vector is something like this, 2t, 3t squares. It means that at time t you are at this point. What will be the velocity at this point, right? So it's just t del f. Okay, so this is vector by vector. This is the this is derivative of the vector by vector. Okay, so this is not called tangent vector. Vector by vector is called tangent vector. If you have vector and you are derivative, you are taking derivative of the vector with respect to vector, that is called a tangent vector. So that will come. So this part is clear. How to take the derivative of a scalar with respect to vector, right?
Yes,
Okay.
sir.
So we have seen a scalar by vector. We have seen scalar by scalar as well. That is easy part. Now scalar by matrix. Scalar by matrix will be what? So scalar by matrix. How to do scalar by matrix? Again, the same thing. You do the numerator layout methods. So this is your scalar value function. Let's say by your scalar value function, and W is this matrix, right? So what you do the transpose of this thing, and this thing remains the same. So transpose of this with the operator. So here matrix was your Their matrix was your W11, W11, W2, W12, and W1D, right? Up to this thing. So if you take the operator, then you will have to transform this. So this all will become your operators here becomes here if okay. So okay, so okay, so here they are coming in the row. In the transpose, the operators become into the column, right? Remember, so here derivative with respect to W11, W12, W1D, right? Similarly, second rows becomes columns here, and the last row become the last column here. And operating upon.
Why is this so?
So this is by design. It's actually there's two ways. Even you can even store as dy by del W11 del dy by d W12 something like that. Again, you can store those things, and this is called denominator layout. So this is the difference of layout only, right? This even you can store something like that, or even you can store something like that. So this is called Hessian matrix, and this is called Jacobian matrix. Okay, so difference is only the transpose. One is another transpose of another, right? So we are following this notations. This is called numerator layout notations.
That's the Jacobian matrix.
Jacobian matrix, right? Right. So now we have seen three methods, three derivative. One is scalar by scalar, that is easy part. Another is scalar by scalar by a vector, right? That we already seen, and scalar by a matrix. That all these things we know. Now, if we find the derivative of a vector with respect to scalar, it just take the element wise derivative. So if this is your vector, then take that element wise element wise the difference derivative with respect to a scalar. Is the font visible to you? I see. Right?
Yeah, this is better.
So, the main thing would be if we do a matrix by vector, what would it be? Because that's the most essential part in our OLS.
Okay, then we are coming to that. We are coming to
Yeah,
that.
yeah. I was just kind of saying it. Thanks.
Okay, so here if we take the vector by scalar, it's just the element wise derivative. So you take the derivative of y1 with respect to w. So it's again the same thing, right? So it's here it's a scalar, so it doesn't make sense. You take the transpose doesn't make sense. So it's just the operator here, and then you operate upon this thing y. So y is your this vector, right? Y1, y2, y up to yn this operators, and you take the that concurrent product of these things. So this will become del y1 del w del y2 upon del w something like that. So it's a scalar, it doesn't make sense, it doesn't affect your value. But if you take the derivative of a vector with respect to vector, so if you take the derivative of this thing with respect to this vector, now the things got trickier, right? So here you have to the same logic you have to apply. You have this by, so you have to take the derivative with respect to this vector. So you have w1 up to wd transpose, right? And here you have to take the derivative of this function by 1 up to by n. Okay, so how you will do that? You take the transpose of this thing and take the operator. So the operator will be del upon del w1. Okay, so let me do it here. So how can I remove every? Can I remove all the ink here? Or then let me do this on this particular. Can you see the whiteboard?
Yeah, we can see the whiteboard.
I think it's not visible.
Sorry,
The blank one, right?
No, not the blank one. Sorry, we're saying the gradient.
So here we are taking the derivative. Here we are taking the derivative of this function. So derivative of with respect to the vector w1 up to WD. This is transpose. This is I'm taking derivative of this y1 to yn, right? So what the logic? You just take the transform and with the operator. So operator will be d upon del w1, del upon del w2 up to del upon del wd, right? And then operate upon this thing y1 up to yn and take the that product. Okay, so that transfer product. So you can see that this will be del upon del w1. Okay, so we share the entire screen. Is my screen visible now?
No.
Is it visible now? So we were calculating del upon del w1, right? So here it is vector del upon del w, and this thing vector is your this thing, right? And if we derivative, so logic says that you just take the operator del w1, del upon del w1, del upon del w2, and up to del upon del wd, right? And okay, so here I have to do the row, right? Because transpose will the transpose of a column will become row, so it will become something like that. So it will become.
We can't see this your whiteboard, sir.
Is it not visible?
It's visible. It's visible, Vasu. It's visible. Has it not refreshed at your end, Vasu? Just check that.
So take the transpose of the whatever variable you are differentiating with. So del wt, and then do the cross-cut product with the function which you are operating. So here we are operating this function y1 up to yn, right? So what will be the cross-cut product? Is just the product element by product. So this will be del. This you think is as a B matrix. This is a matrix, right? So this will become del y1 to yn vector, and with respect to del w1. This we already know, right? With respect to vector yn del w2 up to this will go del, and all these are coming in a one row. Remember, right? These y1 up to yn up to del w2.
Is direct B, or is it the B transpose we are looking at?
No, all direct B.
Direct B, okay.
Right, so this will be, this we already know, the derivative of a scalar with respect to derivative of a vector with respect to a scalar, just element by scalar, right? So this will become del y1 upon del w1 up to del yn upon del wt, and similarly del y1 upon del w2. Okay, so this is w1 only, and up to del yn upon del wn, and similarly del y1 up to del wd. This is 2. Up to del by n upon del w, right? So this become the derivative of a scale of a vector with respect to vector. So this is vector by vector. Okay.
How many columns will be there? N square.
So here will be d into d into d. So this will be
D
n
square,
into d.
N into d. Yeah. Oh, what? That's what n square is. N into d.
So this is n, this is n, this is n, and how many such time d times n into d columns.
Yeah, and sir, if we go back to our OLS, and if I take X transpose W and differentiate it with respect to W, by this logic, I will get X transpose only. No, I will. So when I do X transpose W,
yeah. So by your,
W,
if you apply like something like that. So if you apply del, let's say del w by del vector. So if you using that method here, it is just identity matrix of say d cross d matrix, right? And if I apply del upon on the transpose with respect to weight vector, so it is gonna be trickier thing, and it is something like that. some here it's gonna be some 1 0 0 and then 0 1 0. So I've written down it here. So apply the same thing here. You will see if you take the derivative with respect to W of with respect to W, then you will get the identity matrix. If you take the derivative of W transpose with respect to W, so here it will be something. So this is 1 0 0 0 and then 1 0 1 0 0 and 0 0 something up to 1. So some this vector you will get.
It yeah, that will also be a identity matrix only, right? It will
No, it's not
encode
a identity matrix. Those all are coming in a one row only.
Acha, okay.
Okay.
So this entire question I had asked you because I was trying to figure out if I take XW, X transpose W and differentiate with respect to W, or W transpose X with respect to W, both are the same thing. What will I get? Will I X transpose W by DW? You will get X transpose.
Okay, so
Suppose I do
if you look,
W,
if you want to
if I
prove all those identity, then you have to actually have seen how AW looks like, right? How XW look like, how X transpose W look like. So if you don't know the entities of this, proofing part will be different. And otherwise, I will come to that those identity, and I will try to prove those things as well. Not the proof,
okay.
but I will try how you can do those, right?
Okay,
And so
if you can just tell us how to approach it, because X transpose W I figured out, but W transpose X I couldn't. Right?
Yeah, okay,
Because
we'll come to that. Okay, so
okay.
here we have done vector by scalar, vector by vector. Now next thing is vector by matrix. So all these now things will get trickier, more trickier. Now it will go into higher dimensions. Now, so similarly, you have, let's say you have a vector by of by 1 up to by n, and you have to take the derivative with respect to a matrix. Let's call those W matrix. Capital W is here W11, W12 up to W1. Let's D, right? W21, W22 up to W2D, and all the up to WD1, WD2, all up to WDD, right? So this is D by D matrix. Now you have to take the derivative of del by del matrix. So this is a vector, this is a matrix now. So if you take the matrix, so the same rule, take the transpose with the operator. So here it will be del upon del W11. Now take the transpose del upon del. Here what would be here?
2 1.
2 1, right? Up to del upon del W
D1.
D1, right? And again, same thing here, del upon del 1, W12, del upon del W22 up to del upon del W D2, and up to del, here it will be the last column, right? So del upon del W1D, del upon del 2D up to del upon del WDD. Right. So this matrix will be operated upon now what? This vector. This vector, right? The counter product within the vector by 1 up to by n. Right. So if you look at the dimension here, so here dimension will become very higher. Okay. And again, this will become del upon del W11 with respect to this thing by 1 to by n, and again del upon del W2 to 1 with this by 1 by n 6. So this dimension will go very, very high. Okay. Now, so this is the thing. If you do vector by matrix, and even if you go higher in the higher matrix by matrix derivative, this even goes that become tensor. If you do derivative of matrix by matrix, so the output will be something called tensors. I mean that it's called tensors, or you can think as matrix of matrices. So that becomes more complicated things, but the idea is same. If you are taking matrix, let's say you have matrix by matrix. So here it is by 1 1, by 1 2 up to by 1 n. Here it is by 2 1, by 2 2, by 2 n, and similarly by n1 up to by nn. So this is the matrix, and you are operating along with this again this matrix W matrix. So if you take the derivative here, the derivative will become del by del W, and this will become del upon del W11, and again the constant product, and this product actually goes in the tensor quantity, because here again you take the vector quantity, this vector again will give the Jacobian matrix, right? So this Jacobian again, so this will become matrix of matrices. So this is called tensor. So here we are not going, it's are only that we will use the vector of vector, derivative of a vector with respect to vectors, right? So that's all of our use. So in our particular case, you have to remember these identity. So if I take derivative of A is a constant matrix. It's not a function of variables. So if you take the derivative of AW with respect to DW, remember it's the A. So it's something like that, AX. If you take the derivative of this function with respect to X, what is this? It's just A, right? So here A is a constant matrix, right? So it means that it don't have any variables. So if you take the derivative of this, it will become a things. Okay, and here if you take W transpose A with respect to del W, here again A is a constant matrix. So here it is A transpose. And if you want to prove this, you have to look how the W transpose A look like. So if W transpose
One
W
question. Can we
yes,
actually show why W transpose A is A transpose, or is it going to be too complicated?
not complicated, but you have to just look at the so here this W transpose A, right?
Yeah.
With respect to W, if you do it is gonna be A transpose. So if you look the proof of this, you have to look at the element of W transpose A. So let's assume W is your again W1 up to WT, and A is some matrix called, let's say if, this has to be D cross some matrix, right? D cross n
Right.
matrix. So this let's say A11 up to A12. So here element you have to look. So how the element of W transpose A will look like?
They'll come as a column.
Right. So this is gonna be a D cross. This is gonna be your
D cross
one cross n matrix, right?
Yeah, 1 cross n. Sorry. W transpose is going to be n cross 1, isn't it?
W transpose A gonna be
Will
A
be
1 cross n matrix.
what? So take it as same our lecture this thing. Now, if you take W as D cross 1, then W transpose will be 1 cross D. And A, if you take it as X, it will be D cross X.
Yeah, that's what I'm taking. W I'm
Yeah,
taking
yeah.
as D
Okay,
cross
okay. Yeah, yeah.
1 matrix. So W
Yeah,
transpose
yeah.
will become 1 cross D, and A will become W transpose A will become 1 cross n matrix, right?
1 cross N. Correct, correct, correct.
And
One
how the
second,
element will look like?
Sorry to disturb you, but what you wrote up there, W is equal to brackets and then W1 to WT, it is written as a row. That's the reason why I was a little
Okay,
confused.
so whenever I call a vector, think as a column vector. Vector
Column
is
vector,
always a
okay.
column vector. Okay,
Column
so
vector,
that
okay.
is
All right.
that's
All
my
right.
bad. I should write
All right.
T here. T, right? T,
Yeah,
right.
yeah.
Okay. Now, so how the W transpose A vector will look like? What will be the entry here? Just think, just if you are getting confused, just think as W transpose as W1 up to W1, W2 up to
WT.
WT.
The
And
WT.
here it will A11,
A1, yeah,
A12, A1N, right? Here up to
correct.
A21, A22, A2N. Here it will be AN1, AN2 up to ANN, right? So
Correct.
how this element will be? What will be this
A,
element?
not
One
This
and
will be
A2.
WI, let's say WI, A, what is varying
1
here?
1. Yep.
no, sir.
WI, AI,
It should be A
1.
D1, A D1 to A DN. The last row.
This multiply by this thing.
Yeah. So correct. So W has D features, right, or whatever D, right?
Yeah.
And so a column also
Okay,
should
okay.
be
So here I've taken n by n. So that's my bad.
okay.
So this should be D cross n matrix. So this will be D1
Correct.
up to
Correct.
DN.
I'm just doing this so that it's clear. It's because it's exactly
Yeah,
what
yeah,
our
yeah, yeah. That's
OLS.
the right point. That's the right point. This is D cross n matrix. Otherwise, this multiplication doesn't make sense. right? So this will be this will be this product and this product, right? So this will be W1 A11 plus W2 A21 plus up to WD AD1, right? So if you write it in summation form, it is gonna be or just think something like that. Now you W1 A11 plus W2 A21 plus WD AD1. So this is your first element. What will be the second element?
W1 A1 A12 W2 A22.
Yeah, similarly, right? Now this vector you got. Now you have to take the derivative with respect to what? You vector again. The same thing apply with respect to, so you have to take the derivative of this with respect to a vector, which is W1 up to WD transpose, right? So what is the way? Take the operator del upon del W1 and the transpose of this thing. So here it is transpose, it will become row vector, and del upon del WD and the counter product with the this particular vector, right? This particular vector. So if you go in this manner, you will see again a vector, and if you see here, all the other terms will vanish, right? Because here we are taking with respect to W1, all other things will vanish, right?
Correct.
You will left with A11.
Correct.
Similarly, for the second, you will do so for del W1, right? Again, you will do for the second term with this operator.
Yeah.
So that will left with
A22.
A21.
A21. Correct.
Similarly, A31 up to AD1.
Okay.
Okay, so, and the second operator will apply here. Okay, and at last it will be it is same as A transpose. That's the point, and that's how we saw that this proof, all those proof goes in the same manner.
Okay.
Okay, so remember the basic tricks. How you need not to remember how this proof goes. You just remember if you're taking derivative of vector with respect to vector, this is identity vector. If you're taking A W of DW, it's just A matrix, and if you take D W transpose A, here remember A is a constant matrix with the constant terms only. Okay, so this will become A transpose, and one more identity that you have to remember is that D of W transpose AW with respect to del W, it is W transpose A transpose plus A. Okay, so this proof will gonna be very complicated because this thing gonna be the terms you have to see, you have to be very careful with the terms in this matrix and then take derivative with respect to W. But the proof goes in the same manner. Okay, so these three identity you have to remember. Remember these three identity. Now you can prove our loss function. You can take the gradient of the loss function. So let me do this here. So every step will be clear. So your loss function is a function of a W, right? W is a vector again. W1 up to W1, W2 up to WD. Can you please mute yourself? So loss function gonna be, what is loss function? X transpose W, right?
Yeah,
minus
X transpose W minus Y.
Transpose.
Transpose into the same.
X transpose W minus Y.
Right. So if you solve, if just take the transpose, this will become transpose of X transpose W, which is W transpose, which is nothing but W transpose X minus Y transpose, right?
Yeah.
So this is X transpose W minus Y. Again, if you take the product, it will become W transpose X, X transpose W. The product of this with this, product of this will be what? Minus W transpose XY, right?
Yeah.
Now product of this with this will be what?
Minus Y transpose X transpose W.
X transpose W, and next thing will be
plus Y transpose
Y. Can I write this thing like W transpose X, X transpose W, and this thing as let me write it as 2 Y transpose X transpose W. Can I write These two terms are these two terms same?
Yeah, they are
Okay,
the
you're
same.
shifting the y's. You're swapping the y's and w xy to the front and w to the back.
So what is the dimension of W transpose XY?
W is d1, x is dn.
W transpose is 1 cross D, right?
Transpose is 1 cross d, correct?
X
Yeah.
is D cross N.
d cross n,
This
and
is,
y is n cross 1.
what is the dimension of this?
1.
This is a scalar quantity.
Yeah.
So transpose of a scalar is
Doesn't
again the
matter.
same thing, right?
Yeah, yeah.
So what is
yeah.
the transform of this? Y transpose X transpose W, right? So these
Right.
two terms are same.
Okay.
So I just write 2 times one of these.
Sir, when can we do such kind of interchanging terms when the final output is a scalar, so I can transpose it, or as long as the dimensions match, I can transpose it?
No. As far as they are scalar, then transpose is same. Otherwise, I cannot say, right?
Got it.
So here again, so this I've just simplified that loss function. This is your loss function.
Yeah.
Right now you have to take the derivative with respect to what?
Yeah.
W, right? So remember the so this will be derivative of W transpose X, X transpose W with respect to W. So what will be this? And this will be 0, right? This is a constant. No W here.
Yeah.
So what will be this derivative?
W transpose into XX transpose plus X transpose X.
Plus transpose of X, X transpose.
Correct. So that's X transpose, X transpose X, right?
What is the X, X transpose of this? This is again X, X transpose, right?
X.
So this will
Sorry?
become 2 times W transpose X, X transpose.
X transpose is extra. XX transpose only. It doesn't change. Okay.
AB transpose is B transpose A transpose. Right? So if you apply here, then the X transpose is X.
Oh, the terms also change. Okay, sorry.
Yeah.
The terms
so
also swap.
this will become 2 times of. So this is actually transfer of this thing. So XX transpose. This become 2 W transpose XX transpose, right?
Yeah.
What is the derivative of this thing?
It's going to be
Y transpose W X transpose.
Y transpose X transpose.
So this is your derivative of loss function with respect to the W vector. And what is the gradient in this case? Gradient will become transpose of this thing. Transpose of this thing. Right? So transpose of this thing will be 2XX transpose W minus 2XY. Right? And this is your gradient of loss function. Right?
Yeah.
So you can remember these 3 identities.
Yeah.
These 3 identities.
Yeah.
Sir, you'll
upload this.
Sir, can you just share the screen again, sir?
Which one? This?
Just those 3 identities. Yeah, sir, please upload these slides also.
Okay, I will.
Yeah, thank you. No, these are very helpful because I was struggling with, just for completeness, I was trying to prove and I could only prove half of it. So it was very beneficial.
Okay. But all these things you are supposed to know, and basically if you're struggling with this, that's why I just shown how they can be computed. Otherwise, beyond your course, it's not like syllabus of course where you have to ask to do the derivative and all.
It's good to know how it came about. Actually.
No, just for like, because tomorrow it could be in some other scenario, right? So if we know how the building blocks work, then we can apply it anywhere.
Yeah. Okay, so matrix calculus, I think you must have seen in the math courses. So higher dimension, I mean, how to find Jacobian, how to find ACM. this thing you must, I think you must have seen in math courses. So it's kind of
No,
revision.
Hessian is fine. Hessian is there, but Jacobian we didn't. But Jacobian is just collection of first partial differentiation derivatives. But this kind of specifically, matrix by vector or vector by vector, this thing we didn't go through, which is okay. Just one question: is there any particular Indian, international, any particular textbook which covers this? I tried to look through all the books I have. There was no textbook which covered. I sent you some notes, sir. I mean, that's the only thing I could find, but that was not very easy to follow.
Okay, there is one book I don't remember the name, because I followed in my graduation time. So that book is, I think, it's a calculus book, a standard calculus book. I don't remember the other name of that, but it's called differential and integral calculus. It's the name of that book. Have to see that
Matriskino?
other name.
Differential and integral. Is it like Indian author or?
Not Indian author, it's a foreign author. So don't remember the name. Where it all covers that differential calculus, vector calculus, integral calculus, and this all matrix calculus and all everything that book covers.
So what is this topic called? It's vector calculus only, right?
If you Google it like matrix calculus, you will get lots of reference material.
Okay.
It's just
So is it
different reference material follows different notations and all that sometimes get confused. So
okay?
So I took W just because we are following W as a variable in our case, but mostly you will find X and Y, something like that.
Yeah. So will you try to recall, sir, and let us know?
Can you tell me the title, sir? Once I'm just actually
differential and integral
calculus.
Differential and integral calculus. Just a minute.
Just search different. I'm on the road actually, Ravi. So differential integral calculus engineering.
I'll try to find out the other name and we'll post. We'll let you know in the next session.
Okay. Ravi, you got
Richard Corrant, Clyde Love, Daniel Murray, George Osborne.
There will be many books named
Nikolai Piskunov. That book I heard about. 34 more, lots of things. And in fact, there is a free PDF also. I don't know.
But one more update on the tomorrow session. I will not be available tomorrow. So week 6 section I will take on Monday 8 to 10.
Okay.
And it requires one session on Wednesday 2 to 4.
On Thursday is a submission, right?
Wednesday night is the submission. And
Wednesday
Tuesday,
night is the submission.
Yeah, so Tuesday I don't find any slots available because all is clashing with PDSA, MLF and other courses. So only slot free was Wednesday 2 to 4.
Sunday also you're not available?
On Sunday?
Uh-huh.
Sunday I have to check if any slots available on night. I can take Sunday and Monday. Monday is okay. Monday 8 to 10 I will take.
Monday is perfectly fine. I was, instead of putting it to Wednesday when we have to submit, if we cover it Sunday back to back.
So week 6 is relatively small week. So summary I will try to finish in one session. Next I will try to do the programming of week 5 and week 6. So we haven't seen the programming of week 5 as well, right? So that part I will cover in the next session. I mean,
week 6, are you sure it is small? There's so many videos there.
There's an lasso, right?
Yeah, lasso regression, yeah.
There's regression and lasso regression. So sir took the path using that. Sir started with the probabilistic view of the linear regression and then do the Bayesian estimation as well, and then reach to the ridge regression and lasso regression. So let's see how we'll try to finish in 2 hours.
I think this has been a constant request in most of the recent classes. Just before the quiz we started off, practice problems, any book you can cite to us, it'll be good actually. When you solve this kind of a thing, like a problem like you just did, it hammers home the point better.
Yeah, but I didn't find any book which covers such questions, which had such questions.
Okay. Anything from any of the exams in the institute? Not the complicated ones, at least the easy ones that we can probably.
Sure, how we can find those questions. Such books I never come across with. So probably you want to record some data mining books. If you go for, so I think I should stop recording this.